Hello, I'm Klaus Schliep and I'm a postdoc with you in Ravello, and it's also collaboratively kind of pushing me with ideas on this talk. And so we'll talk about some problems with model fitting and model selection, or the analysis of discrete character evolution. So it's kind of comparative methods, but also phylogenetic estimations. And yeah. I will also talk a little bit what I think is really important to have nice exploratory data analysis and having some nice plots. So this is here these famous textbook example of these enscoms for it's kind of 4 little data sets, just 2 variables x and y, and each of these variables, just looking at them, tells a very different story about the relationship to these 2 variables. But the problem is, if you actually draw a regression line, it's exactly the same, and it's not only that the correlation is the same, you can look at the R square and kind of pretty much every statistical parameter on this little data set, and they seem to be exactly the same. Even kind of you really have, if you just look at the data, they're telling a very, very different story. So kind of testing from time to time during your analysis, it's really kind of important to really look what the data actually look like. And in statistics, you normally, in the end, maybe have even only some tables as your results, but in between, you probably made a lot of plots. So, one of the problems is we kind of have a process like just the talk before, kind of 2 characters. It could be a habitat, and they kind of, these characters evolve along a tree. So that's here how the process is kind of generated. And when we kind of then, but of course, usually we don't really have all this history. We kind of just see kind of the results we observe at the tips, and we also estimate a tree. So the problem is, and that's kind of the normal thing in comparative discrete comparative analysis, is kind of just trying to estimate this process. And of course there's a lot of different software packages around where you can do this, and you get a result which looks like this. And that's kind of the R package Geiger, but there's probably a lot of other different packages there, and it gives you some results, but these results by themselves are not really meaningful. So what is the likelihood, or what is the rate matrices alone doesn't really tell you anything about your data. So it's again important to do what really would look this process like, and of course I'm using Phytools for this and generated a stochastic character map, and then we see, oh, this process seemed to be very, very different to the process where we generated the data from. And so we can ask ourselves, what's causing this difference? Since we know how we generated the data, we don't really want to estimate now a rate shift or something else which may can save our thing. But we kind of, what I will highlight is, it's really, if you look at it, so now I hope you can still hear me. What's causing one of the problems are these kind of what I call cherries, or which are called cherries. That's kind of 2 taxa which are connected together, and there's a few of them which are very short. And the problem with these short cherries is they pretty much dominate how you estimate your rates. And to do this, we can kind of just made a so-called leave one out analysis. So we have these 3 with 50 taxa, and we kind of just prune away each one edge at a time and estimate for this kind of now slightly smaller data set the rates. And we'll see that we can easily see when we prune away one edge, for most of them, or we actually not edge, we prune away one tip. And if we prune away each tip, most of the time it doesn't matter, but it matters for kind of 3 or 4 positions. And that's, again, all our cherries again. And we see if we have here, this cherry actually has 2 different states. And that causes the enormously high rate for this. And if we prune away one of these elements already, the rate is a kind of a third than we would infer otherwise. And if we would prune away one of the other cherries or one of the tips in the other cherries, the rate would actually get much higher then. And that's kind of a little bit worrying because the rate we estimated was 10 times higher than the rate we were simulating the data. And I think it's probably useful to look more in some of these analyses when also estimating models like the SPAM to see if not only kind of an AIC value or a BIC value suggests that the regime to construct it, but also if the analysis is robust, really what happens if we prune away a few texts. So you may also just do it like in the first talk in the session, prune away, make kind of instead of a leave one out, just randomly choose a 10, or just choose always a tenth of all the taxa which you get rid of and see if you still kind of get a very similar estimate. So that was kind of the first part of my talk. Now, the solution. So cherries are extremely influential, so you really have to take care if you pick cherries. And yeah, the leave one out analysis can really help to see if there's kind of influential variables in your data set. And yeah, it also seems a little bit that kind of the estimates we really get for these rates are maybe not really statistical efficient because we have this kind of weird dependence on the very short edges. So getting just more data for trees is maybe not really helping too much. So the next part is kind of partly inspired also by a really great talk, I think it was last year, from Mark Brewer. He gave at the Methods in Ecology 5th year anniversary symposium, which he called Model Selection and the Cult of AIC. So Mark Brewer is a statistician and he realized biologists kind of compare models only most of the time with AIC. And so let's look at these AIC criteria. And the AIC is defined as the negative log likelihood plus 2 times k. K is the number of degrees of freedom of your model. And the BIC, that's kind of a small variation. It has this log n term, but log n is usually kind of a constant. And it's just a constant which is usually greater than 2, so we are penalizing our likelihood function slightly more, so we usually get a more parsimonious model back. And then there is this AIC variant, which has a slightly more complicated formula, which is kind of a finite sample correction. So if you have smaller sample sizes, this is supposed to be very good. And so the n is the sample size and k is the number of degrees of freedom. But the problem is all these models were derived for kind of regression models or linear models. And so it's actually, I think, even these other textbook formulas, it's good to add here another parameters because k must be kind of smaller than n. The problem is in comparative methods, we would refer to the sample size mostly as a number of taxa. With tree inference, things like model tests, there is a kind of a huge variety of options. Most of the time it's the number of sites we have, but can be the number of sites times the number of taxa. I think that's what Smiga is using. You can also throw in the Shannon entropy, and there's kind of a huge array of things which kind of keeps you wondering if it actually any of them is good. And then of course the other problem is the number. To estimate n and k, you usually assume that your parameters and your variables are uncorrelated, and of course if you do have this tree as a structure, you actually assume that they're exactly not correlated. So all these estimates are a little bit tricky to compute. And for example, you think of very simple things for number of trees is how to count the number of edges. But it's actually not so simple, because often you have sequences which are identical, and if you have identical sequences, well, then you have quite often kind of three options. You either get a binary tree, that was every tree program to estimate a tree most of the time returns, but all these red edges are actually of size length 0, so you can actually prune them away, and so you can make just kind of a multiplicating tree, or just get rid of them all and only one representative. And so if you have a data set, it has kind of 133 tips. It's kind of a data set of some fish from Rita Castillos, who sits in the end of the audience. And if we use the whole tree, we have 259 edges. If we prune away these internal edges, then we have 197 edges. And if we kind of prune away all the duplicate sequences, we are left with 93 edges. And if we would use the AICC value, then actually the order of our models may change. Even the likelihood for each of these three trees, because all the edges are 0, is actually the same. And even more worrying is that we have kind of this problem which I was telling, if we are not looking at that k is always smaller than n, then first kind of the penalty grows the closer we get. But if we just, for example, take the number of sites as our n, we can have actually trees with 500 taxa for alignment from one gene, which has maybe 200 sites. So we are actually on this reward system side, where we actually get, for more parameter we are using, we would kind of get exactly the opposite of what we want to do with ASC, to penalize too many parameters. So that's kind of just some warnings. So simple transfer from one kind of likelihood method, which is to phylogenetics, it's probably not working. There is some nice theory about how to get number of parameters in a penalized likelihood framework, which is probably really important. And I think it's also really important every step look at your EDAs, and it's really time for more recreational math, as it was called with Susan Allman, I think, Elizabeth Allman last year here. So it's work together with Liam, and also discussions with David Posada. The data come from Rita Castillo, and maybe time for one question.